Okay everyone, this is the What You Need to Know video about Unit 2's rational numbers. Watch this as often as you need to make sure that you understand everything that you will be asked to do. So what's a rational number? Well, the basic definition of a rational number is that it is a number that is locatable on a number line. That means it has a fixed address. Okay, but this doesn't really say a whole lot, which I completely understand. So let's think about types of numbers and categorize them. There are two types of numbers. You have real and what are called imaginary. In 7th grade, we focus only on real numbers because, well, hey, it's numbers that you can actually see and work with. Within real numbers, you have two different types of numbers called rational and irrational. Irrational numbers, as you can see over here, there's only one basic category of that. However, in rational numbers, you can further subdivide these into integers, whole numbers, and ending with natural numbers. So let's define some of these vocabulary words, and then you can go back to that graphic and it may make more sense. First, real numbers, like I said, encompass all of the numbers that you know about. There is something called imaginary numbers, but you don't work with those until you take Math 2 in high school. It is designated with a lowercase I, which kind of looks like a variable. All rational numbers have a home on a number line. I like to call it a fixed address. In this number line, you'll see multiple different examples of integers, which, as we've defined, are positive or negative whole numbers. Whole numbers, which, well, hey, they're numbers that are whole. You have natural numbers, which are your counting numbers beginning at 1, 2, and 3. And then here you have rational numbers. Rational numbers also include fractions and decimals. I just noticed a typo here. Whole numbers do not include negative integers. They only include positive ones. So I am sorry about that, but that graphic, I just wanted to make sure that it got fixed. Whole numbers, integers, natural numbers, fractions, terminating decimals, or repeating decimals, all can be placed on a number line in a specific location, whether they are positive or negative. Let's now look at irrational numbers. They can be written as a decimal, but they never end, and they don't repeat. The easiest one to remember is pi, which is the ratio of the circumference of a circle to its diameter. We're going to work a lot with pi later on this year, but you can easily Google pi online and you'll see the first million digits, and there's no way that there's really never been an end that's been found. That's why we call it to infinity, which is the symbol in the classroom. Now let's look at rational numbers that you will work with in this unit, as they include positive and negative ones. But in this instance, we're going to increase our load from integers and go with fractions and decimals using the 4 basic operations. The mental model for determining if an answer is positive or negative is the same as it was for integers. I cannot emphasize that enough. This model works for adding and for subtracting. You can use the debt model that we talked about this past week. I know those of you in 7+ in the afternoon didn't get that. I'm going to go over that this upcoming week in class with you. let's begin with a decimal example. When adding or subtracting decimals, line up your numbers using your graph paper. This is just simple computation we're talking about. I'm going to do a quick review of positive decimal operations with no negative numbers first. This part is reviewed from 6th grade, but if you're rusty, please pay special attention. Let's look at this number, 3 and 1400ths plus 2 and 187 thousandths. I lined them up vertically. I made sure that my decimals are all lined in a single line. Notice that the decimals are located at the intersection on graph paper. They're not in the middle, kind of flying or kind of over here, or I've seen even examples where they're up here. They don't need to float. They can be on the floor of the graph paper. Anyway, load this up. Notice that my place values are lined up. Now, there isn't a number here above that 7. That was because there wasn't a digit in the thousandths place. It's understood to be 0. If that confuses you, feel free to add a 0 here because that will not change the value of your answer. So, if I do add a 0 here, I can then just add normally. 0 plus 7 is 7. 4 plus 8 is 12. Carry my 1. 1, 1, and 1 is 3. 3 plus 2 is 5. My answer ends up being 5 and 327 thousandths. Now let's look at this using those same numbers to subtract. Again, I lined them up, but in this instance, I must add a 0 because I cannot take 7 away from nothing. That's not going to work. So, I add a 0, borrow from the 4, this becomes a 10. 10 minus 7 is 3. I'm left with a 3 here. I have to go over and borrow from this 1, which makes it a 0. 3 plus 10 is 13. 13 minus 8 is 5. Now I have to repeat this process over here. I have borrowed from the 3, make that a 2. Add a 1. 1 minus 1 is 0. My answer is 53 thousandths. Oh, sorry about that. I made a mistake. And I'm not going to go back in my video here, so let's pretend that didn't happen, and we're going to play it again. Just watch the normal subtraction. The answer is 953,000. Sorry about that 0. I know I got distracted. But 10 minus 1 is 9, which is what that number was here. In fact, I'm going to go in and clean that up just a little bit so that it is right. You might be laughing at me or think I'm crazy. That's okay. It's totally fine. Now let's look at multiplying and dividing decimals. Here you can use the traditional method or the lattice method. It doesn't matter if you line your decimals up. That is a common error that kids make. They get so fixated with adding and subtracting them that they feel like they have to be lined up. That is not the case. They don't. Let's look at the next example. In this one, I've got 2 and 13, excuse me, hundredths times 2 and 643 thousandths. I have now shown traditional multiplication, and now I'm setting up the lattice grid, plugging in my numbers. You do not need to know both ways, you just need to know one way. The main thing I want you to take away from this is the location of the decimal in the final answer is determined by the place value that is included by the sum of all of your digits in your question. So here I had 1, 2, 3, and here 4, 5. That means I have to move my decimal 1, 2, 3, 4, 5 here, and that leads me with my answer, as you see. Same thing over here with the lattice. I started here and worked my way up until I got in between the 5 and the 6. If one of these numbers in the previous question was negative, then the answer would have been negative, using the same multiplication and division rules as we worked with using integers. If both numbers in that example had been negative, we would have ended up with a positive answer. Again, just like we would have if they had been integers. When you are subtracting decimals, especially if you have a negative answer, or you're working with a negative number, think of colors like with algebra tiles, using red and yellow, or red and green, some combination thereof. Here's an example. Let's say I have 1 and 27 hundredths minus 6 and 94 hundredths. Since the second number is larger, the answer will be negative. You can visualize this on a number line. If I had a number line here, this was 0, this was 1.227 hundredths. I have to move that way 6 and 94 hundredths. If I continue, I have to find my location. It's going to be left of the 0 until I reach it, and it would go off my screen over here, and I have another number line down here, and this shows you my final answer, which is negative 5 and 67 hundredths. Here's another example. Let's say I have negative 10 and 46 hundredths plus a negative 9 and 43 hundredths. Visualize this like algebra tiles, or again use the number line illustration. I'm adding a negative and another negative together, which is going to give me this answer. This is saying that I'm 19 and 89 hundredths away from 0 and the negative side of a number line. Here's yet another example, 12 and 3/10 minus a negative 2 and 6/10. Like in the integer rules, subtracting a negative changes it to a positive. So I rewrote my equation over here, lined up my decimals, and then added normally. 12 and 3/10 plus 2 and 6/10 gives me a final answer of 14 and 9/10. Now, let's switch gears and go from decimals to fractions. Remember that when you are adding and subtracting fractions, you must have a common denominator. You figure that out by using the ladder method with least common multiple, or by listing your multiples. Some are pretty easy to determine, others not so much. Just remember, however, that if you're adding and subtracting, they have to have common denominators. In this example, I have negative 3/4 plus 2/3. I can't add those two together as is. I need to convert them. My least common multiple of 4 and 3 is 12. Now I've created equivalent fractions. Negative 9/12 plus 8/12. If I visualize this on a number line, I started over here at 3/4. Here's 0. I'm going this direction 2/3. Since 2/3 is less than 3/4, I'm still going to have a negative answer, but I'm going to end up being a lot closer to 0. And notice that this illustration I just drew is not to scale. So don't be like, that doesn't make any sense. It's not to scale. If you have difficulty thinking of the common denominator, you can use an area model to add and subtract, which is pretty cool. This is something that is taught in elementary school. Maybe you will remember it, maybe you won't. But let's look at the illustrations being shown. The first illustration is 2/3. The second one is 3/5. The only way that this can work, however, is if both fraction squares, or rectangles in this instance, are the same size. This illustration here shows the combination of both models added together. I then went in and I colored where the original shadings would be, but I did change this one into a purplish color so that you could see it. All right. In adding these two fractions, if you count all of these numbers up, you will find that the final answer is equivalent to what I ended up with here, which is pretty cool if you think about it. My final answer was 1 and 4/5. That means that 1 whole and then 4/5 of a second whole would be added together, which is kind of cool. area models may be a little bit confusing because in this one, since you ended up with a simplified answer that created a mixed number, you would have to take a whole out. But I did want you to have some sort of visual that helps you understand what adding the fractions are actually telling you to do. Now let's switch gears to multiplying these fractions. Multiplying fractions do not require you to make a conversion because multiplying fractions actually are telling you how much shared area the two fractions being multiplied have. So in this example, 3/4 times 5/6, yeah, it ends up being 5/8. But the 5/8 is telling you that's how much area both of these fractions share. The next slide, as I'm pulling it up, will show you a good graphic of that. So if you will watch as this plays out on the app, the reason you can have an answer you get is equal to the area both fractions share, as I'm showing. Okay, 3/4 times 5/6 just multiplied out together is 15/24. We'll check it out. I have 24 squares. The yellow delineates my 3/4. The purple delineates my 5/6. Well, guess how many total little squares there are in the big one? 24. How many little squares have both purple and yellow shared? 15. That's my answer. Now, of course, this one could have been simplified to 5/8, but that's only because that is a simplest form. This picture represents why my answer was 15/24. Hopefully you did some of that last year in 6th grade or even in 5th grade. But if not, watch this part over again so that you can see why multiplying fractions yields the answers that it does. Now let's switch gears over to dividing fractions. This is a review from 6th grade, but I know that lots of kids don't understand why they get an answer that sometimes is larger than the two numbers they're even dividing. This is because when you divide a fraction, the answer is how much of that second fraction fits inside the first. Here's an example. 3/4 divided by 1/3 equals 2 1/4. Now what I just showed was cross multiplication. I usually showed this by showing an overall arc. You can do the copy, change, flip method too, that's fine. Some teachers say you multiply the fraction by the reciprocal of the second, which would have been 3/1. Any of those methods work. You end up with 9/4, which simplifies to 2 1/4. But let's see what that actually looks like. In this model, I've got 3/4 and 1/3. How many sections of 1/3 fit inside 3/4? Well, 3/4, you can see it right here, is just delineated. And think about how many of these red blocks can fit inside it. We have 1, 2. That's where the whole number 2 comes from. And then this little part here is one size big. How many sizes is left in one of these red blocks? 1, 2, 3, 4. So my leftover is 1/4. Now, let's look at a mental model to think about subtracting and adding negative fractions. In this instance, I've got -2/3 minus 1/2. In that instance, I'm starting at 2/3 and I've got to go to the left 1/2. That leaves me ending at -1 and 1/6. My improper fraction answer was -7/6. I just gave the initial answer on here as the reduced mixed number. Here's another example with -1/3 plus 3/4. I have to convert them. My least common multiple is 12. Now I've got -1/3. I've got to go to the right 3/4. So if I visualize that, I need to figure out where I'm going to go. And that requires me to cross 0 as shown here. And my final resting place is 5/12, even though I started in negative territory. It's because I had to go to the right 3/4 of the way. You can see that. Oh, sorry about that. You can see that going here, starting on 1/3, crossing 0, ending at the 5/12 spot. Ask you if you have any questions in class. Like I said, also watch this again. We're going to work with this in class extensively over the next 2.5, 3 weeks, but this should give you some preliminary information. Thank you.